component. To measure the input offset voltage, the first thing we have to do is put the same voltage on both inputs. Because it's such a small measurement, we need to put some gain in here. So we can go with the 10 ohms at one side and 10k on the other. This will give us a gain of 1001. I built that circuit on the breadboard and I'll see what the offset voltage is of various op amps. I'm going to power them all with a plus or minus 15 volt supply. This is a UA741 op amp, and you can see the output voltage is 1.15 volts. That gives us an input offset voltage of about 1.15 millivolts. 1.15 millivolts, that's way too much for a 0.4 millivolt signal. I'm going to take that one out. I'm going to go with an LM308, which is about 0.2 volts, so that's 0.2 millivolts, which is 50% of the signal level. Pretty bad. I'm going to take that one out there. And next is an Analog Devices OP07. These are pretty good op amps. Now we're reading about 14 millivolts, which gives us an offset voltage of 14 microvolts, which is about 3.5% of the signal. I'd imagine for this preamp they're looking for input offset voltages of below 0.4 microvolts. That's about 0.1% of the input signal. That's going to be a lot of work. So now we understand it a bit better, we're well placed to start diagnosing what's actually gone wrong with this thing. Now if you enjoyed that little educational snippet, there's far more of this coming on my new training course I'm building for the Mend It Like Mark community. Check out the links in the description below. I'm going to start by removing the entire top layer, which is the right channel, because there's nothing wrong with that from what we can tell. I'm going to solder these sockets off the board. Start with the ground. They didn't put up much of a fight. Just unscrew these standoffs. They come off quite nicely. Need to undo this mess. Well, something's pulling the positive voltage rail down, which will be something that's gone short circuit, which is something that these little tantalum capacitors are very good at doing. And they're everywhere. But hello, I think we have a clue. That nylon nut looks pretty cooked to me, and that's IC5, and that is right at the beginning of the circuit. It's a 7818 regulator. A part he hasn't ground the numbers off, and that regulator board supplies this op amp board here. I want to disconnect the output from this and see if the fault's just on the regulator board or outside of it. I need to get to the underneath. So I'm just going to unsolder terminal C. There we go. Put this back on there. Just set the power supply up for 28 volts. I'll give it a current limit of 0.5 amps. And I need a common ground. Positive supply and the negative supply rail. Put a negative rail on there, positive rail here, and the ground on the black one. Power it on. Let's pick up the ground from here. Let's check the output voltage from this. There we go, plus 15, and over here minus 15. That's not great news, so there's a short on the fancy op amp board. So I'm going to have to take this off again, so I need to remove the negative output, which is terminal E. So I can remove this off the 28 volt input, connect it to the supply to the op amp board. But we need to change the voltage to 15 volts, and I'm going to knock the current down to 0.2 amps. Let's check we've still got the short. Oh yes, look at that. So I need to get this off. Need to unsolder these wires as well. It's all slowest on the ground connection. There we go. That was hot. Let's have a look at it. Okay. Just going to remove this ground connection. It's going to be a bit more room. This board's actually attached by 8 wires down there, and that looks to be quite a nuisance to keep in line. So I'm going to unsolder this in one go, hopefully. I'm going to be using this 10mm blade tip. Get them all at once. Just going to flood it with a lot of solder. Make sure I've got good thermal contact. Should be less chance of damaging the pads. Just see if I can clean these up. And clean these holes out whilst I'm here. Alright, pin 4's not playing ball. I think it has got damaged. It looks like I've damaged the through-hole plating. Now, I'm going to have to fix that because of the way this is all soldered together. Luckily I've got some rivets which are ideal for repairing this sort of damage. They're a little copper tube that's flared at one end. And the first step's rather painful. I'm going to have to drill that out. I'm just going to use a little handheld drill. So I'm now going in with a 1.3mm diameter drill. I'm just going to finish it off and open it up to 1.4mm. Just going to clean some of this flux off here. Just looks a bit of a mess. I should be able to just push this rivet in. Just rest it on this little base with a little recess in there and just press it down. And just flare it over a bit. And now just flatten it off. Just going to put a tiny bit of flux on there. And just run a little bit of solder under that copper rivet. So we've already established we've got a short circuit here on the positive rail. There it is. And here, 1.8 ohms. The problem is finding out which one, because there's a lot of things connected to this positive rail. All of the chips are on there, all of these capacitors are on there. Could be any of them. So the quickest way to find the short is power it up and see what's getting hot. So with 200 millivolts we should start to see something getting warm. We've got some heat going on. You can see there the 4 chips glowing. And what is that on the top? That's a tantalum capacitor. And it's this one here, C12. We check where it is in the schematics. There it is. It's on the power supply for IC4. 10 microfarad tantalum cap. Well, it's interesting, it doesn't show any signs of thermal distress, but that's possibly because the power supplies near must be current limiting. Well, I don't think there's going to be anything fancy about this tantalum capacitor. Even in this, unless I've had it blessed by the Pope or something. You never know. I'm sure I'll have a tantalum cap knocking around here somewhere. Yep, here we go. Perfect. So that should just drop straight in. There we go. Just solder that in. Get the ground on first. Takes a little time because it's got to heat up all of that copper surface area. And then this one. We'll just check if we got rid of the short. Well, that all looks pretty healthy to me. All the chips glowing evenly and no hot tantalum caps. Just going to line these pins up. There we are. Well, that's typical where I put that rivet. There's no wire in it. Now'd be a good time to replace all these broken plastic bits. There's a little socket head screw in the bottom of here. There we are. I'll just unwind this. And put a new one on. And now's also a good time to reconnect these wires. Poke the white one in there and the red one in there. Always come out again. There we go. Just fasten this down to hold it still. Now I can pop that back on. Now it's a very good time to solder these connectors back on. This is the left input. And now the left output. There we go. Now it's a good time to test that left channel. Have I fixed it? Don't know why I plugged that one in. Well, that looks a lot more healthy, doesn't it? Just check this actually amplifying. Oh, look at that. I reckon that's good. Now I can put these standoffs back in. I've replaced the broken ones. Then put our shielding back on. This is probably to reduce crosstalk, I imagine. Then more standoffs. Got a snap screw thread in this one. I'm going to have to extract that. Although if it being plastic, just line a flat blade screwdriver up. Then heat it up. Just let that cool down. Let's just put the right hand channel back on. Bit of wires going everywhere here. Oh, and these 15-volt regulators don't sort of sit nicely. Just have to put the screw in. Just soldering the input socket. Just got to clean the end of this red wire up. It won't go in the hole. There we go.